Stop worrying about homework and start learning with confidence. This is Ask Learn. Complete help for every subject. Like, share, subscribe for daily learning videos.
Hello. In this problem, we want two different particles to travel along the same circular path in a mass spectrometer. So we know that the radius of the circular path that a particle will travel in a mass spectrometer is given by mass of the particle times velocity divided by the charge of that particle and the magnitude of the magnetic field through which the particle is traveling. Now, we're considering two different particles, a beryllium-7 ion and a beryllium-10 ion. They both have the same charge, they're singly ionized, but they have different masses. So, ultimately, we can write out the expression for the radius that these will travel through in terms of their respective masses and velocities. And then, since these need to hit the same detector a same distance away, those radii need to be the same traveled for each of those particles. So, what I'm going to do is use a subscript of 7 for beryllium-7 things and a subscript of 10 for beryllium-10 things, but we want the radius for those two to travel to be the same. So what is this going to look like? Well, for the radius of the beryllium-7 atom, we have the mass of beryllium-7 multiplied by how fast it's going in the mass spectrometer, divided by its charge, which we'll do as a plus E charge. And then we have the magnetic field through which it is traveling for that particle. Now we can do the same thing and set them equal to each other for the beryllium-10 ion. And I'm going to use a subscript of 10 for that. Right, so they both have that same plus E charge. I'm going to put some parentheses around this. And then it's going to be traveling through a different magnetic field. And it must, because we have to alter the field such that it still curves around the same radius in our mass spectrometer. So ultimately, what are we looking for? We're looking for this new magnetic field that we need for our mass spectrometer to make sure that that beryllium-10 hits the same target that the beryllium-7 did. So let's rearrange that equation and see what we ultimately need to solve for. So let's solve for the magnetic field that the beryllium-10 ion is going through. We'll notice that when we set these equal to each other, our charges actually cancel out. So those are going to go away. So that's nice. So let's keep writing this expression for beryllium-10. When we do that, we see that we have... This is going to be equal to the magnetic field that the beryllium-7 ion travels through, multiplied by the mass of the beryllium-10 ion, the velocity of the beryllium-10 ion, divided by the mass of the beryllium-7 ion, divided by the velocity of the beryllium-7 ion. Yes, that is our expression. So basically, we have to figure out the ratio of the momenta of these two ions in order to figure out how we're going to scale up or down that magnetic field so that these two particles hit the exact same spot on the detector. Now, then that tells us what we really need to figure out, since we don't know the velocities of these particles, is a relationship between the two velocities. But we know that they go through the exact same potential difference to be accelerated up to a particular velocity. So what does that mean? That means that the potential difference that both of these charges go through in order to be accelerated is given by the charge multiplied by the potential energy that these two lose when being accelerated is given by the charge of the particles multiplied by the potential difference, and that is going to be equal to an increase in the kinetic energy of our particles. Because these two have the same charge and go through the same potential difference, that means this value is the same for each particle, and therefore this gain of kinetic energy is the same for each particle. So we can write out 1/2 mv squared, the change in kinetic energy, the gain in kinetic energy, for each particle respectively. And these two have to be equal to each other. So that's going to give us a relationship between the two velocities of our particles. So let's write out the kinetic energy for each ion. So the kinetic energy for the beryllium-7 ion will be 1/2 the mass of the beryllium-7 ion times the velocity of that squared. And we know that they're going to have the same kinetic energy for our beryllium-10 ion, and that's going to have a relationship like this. So we see we have a direct relationship between our two velocities. So if we solve for one of our velocities, the velocity for beryllium-7 or velocity for beryllium-10, and then plug it in to our equation for the magnetic field magnitude that we're looking for, we can see that we're going to be able to get our answer. So why don't we go ahead and solve for the velocity of the beryllium-7 ion. So if we do that, well, I'd have the velocity of beryllium-7 squared. Our halves will cancel, and we're left with the velocity of beryllium-10 squared multiplied by the ratio of the masses of the two ions. Then when I take the square root of both sides, you see that I'm left with the velocity of the beryllium-7 ion is going to be equal to the velocity of the beryllium-10 ion multiplied by the square root of the ratio of the two masses of the two ions. Cool, now I have a relationship between the two velocities, and then I can plug those back in. I can plug this value right in here, and then we'll eventually be able to solve for the magnetic field magnitude that we're looking for. So let's go ahead and plug all this stuff in and see what it looks like. Well, the magnitude of the magnetic field needed for the beryllium-10 ion is the same as that needed for the beryllium-7 ion, multiplied by a ratio of the masses. And then we have velocity 10 divided by, we're going to plug in what velocity sub 7 is, and that's going to be V10 multiplied by the ratio of the square root of the masses. Now what's nice here is we see that these velocities cancel, and since we don't know them, now they go away, and we're not hindered by that to solve our problem. So, to do a little bit of mathematical simplification, right, we have our beryllium-7 here. We're going to then flip the reciprocal of the square in the bottom, and so we have the ratio of the masses, not squared, is going to be multiplied by, not square rooted, is going to be multiplied by the ratio of the masses, square rooted. And we can simplify this square root with some math. We can take the non-squared, put them under the root as squares, and simplify. So ultimately we get this expression here. Okay, so now to find the magnitude of the magnetic field that the beryllium-10 ion needs to travel through in order to hit the same target, we just take the magnitude of the beryllium-7, the magnitude of the magnetic field that the beryllium-7 ion travels through, and then multiply it by a ratio of the masses square rooted. So since I'm running out of room, let me just clear this out real quick. I'm going to rewrite the expression, and then we can finish up the problem. So the magnitude of the beryllium-10, the magnitude of the magnetic field of the beryllium-10 ion goes through, the magnitude of the magnetic field of the beryllium-7 ion goes through, multiplied by the ratio of the masses square rooted. So let's write that. What is the magnitude of the magnetic field that the beryllium-7 ion travels through? 0.283 teslas, multiplied by the square root of the masses. The beryllium-10 ion is 16.63 times 10 to the negative 27 kilograms. And the mass of the beryllium-7 ion is 11.65 times 10 to the negative 27 kilograms. Put all this in our calculator, and we get our answer that the magnitude of the magnetic field of the beryllium-10 ion needs to travel through in order to hit the same detector is 0.338 teslas. And that is our answer.